So this is the course that I teach back home. It's a course called CS50, or Computer Science 50, which is our introductory course in computer science. It's mostly non-majors, students who don't intend to study computer science, but it's also for majors as well. And the goal is to provide students with a foundation in the ideas that underlie computer science, and also very practical programming experience, so that after just a few months' time, students not only understand how computers work and what you can do with them beyond the familiar Google Docs and social networking and the like, but how you yourselves can program them, or how you yourselves can program the mobile devices or phones that are now in all of our pockets. So I thought what I'd do today is give you a sense of what computer science is, because to be honest, I wish I had better understood myself back in high school or even back in college what it is, because at least when I was in high school, I never studied computer science, and my first year of university, I did not study computer science, and that was largely because I was turned off to it. I still have memories in high school of walking through the hallways in my school, and some of my friends, some of my geekier friends, were taking computer science classes, but they had their heads down, and they had these big old desktop computers, and typing away, and focused only on the monitor, and honestly, it seemed not at all of interest to me. It seemed very antisocial and just very technical. And indeed, if my freshman year of college, by then I felt that computer science isn't really for me, because I haven't been taking it since I was in high school or since I was a younger student. And it was only my second year of university that I got up the nerve to set foot in this kind of classroom, CS50 itself, when I was a student. And even then, I only started taking the class because the professor allowed me to take it pass-fail. So instead of for a letter grade, A, B, C, I instead took it initially only pass-fail. But it opened my mind so quickly. And for the very first time in university, this class, CS50, this Introduction to Computer Science, truly homework was fun for the first time in 19 years. I think I'd always tried to do well in school, but I did so because I felt I had to, not because I wanted to. And so for me, this happened to be the first field I discovered where I had this true love. And so what I thought I'd do today is try to give you a sense of what this field is, so that ideally you might consider taking one or more classes in computer science next semester or beyond. So what is computer science? Back in the day, I assumed it was just programming, and it was just one person programming a computer. But it really is more generally than that about problem solving, solving problems. And we usually use computers to solve those problems because we can do it ever more quickly using computers. But it really is just this process of having input and output, or entrada and salida, whereby you have some problem to solve, your input, and the goal is, of course, to get some solution to that problem. And the black box, the square in between, is hopefully the process by which you ultimately solve that problem. But before we can have inputs and outputs, we all have to agree how we're going to represent that information. And certainly a computer has to know how you represent information. But odds are most of you know that computers probably only speak what language or alphabet? So binary, or zeros and ones. So why might that be, or how does that work? Well, that'll be among the goals for just our first few minutes today, to finally teach you all binary and what it is to be a computer and speak this language called binary. So if you consider how we might represent any inputs to a problem, let's consider the more familiar thing that we do in the real world. If you might want to count the number of people in this world, we might do 1, 2, 3, 4, 5, and then I could use another hand or feet or the like. And this actually has a more technical name. This is unary, whereby you have the ability to just put a finger up to represent one person, put two fingers up to represent two people, and so forth. Unfortunately, on at least one hand, I can only count so high, only to 5. So there's better systems that we use in the human world, not so much unary, but instead decimal. Dec meaning 10, or decimal meaning 10, because we have 10 digits, 0 through 9. So this is, of course, what we all use in the human world. But computers, of course, only have 2 of those digits. So instead of decimal, they instead use binary, bi meaning 2, referring to the fact that you only have 2 letters in your alphabet, zeros or ones. And yet, clearly, computers can not only represent numbers like 2 and 3 and 8 and 9. They can represent letters. They can represent images. They can represent audio. So how do you get all of today's familiar features from just zeros and ones? Well, let's actually start with what all of us probably take for granted when representing information, not in binary, not in unary, but just in this decimal system. So this, of course, is what number? 123, right? Sort of goes without saying, but really we're just all looking at three symbols on the screen. One kind of looks like this, the other one kind of looks like this, and another symbol looks like that. But all of us humans here just instantly assigned meaning to each of those numbers and sort of deduced that, oh, that's 123. Why? Well, all of us went to school early on and were probably taught a certain system. Well, what was that system? Well, early on, you were probably taught to represent the 3 as being in the ones place or the ones column, and the number 2 is probably in the tens place or the tens column, and the 1, of course, is in the hundreds place or the hundreds column. So what is the very rapid math that we all just did? Well, you probably did 100 times 1 plus 10 times 2 plus 1 times 3, which of course then gives you 123. Now, none of us actually do that step by step because we all just take it for granted, but that is the system that we all use every day and sort of take for granted. Well, it turns out computers aren't all that different from that. They just have different placeholders. And so consider how we might represent slightly different numbers here instead. In our human world, we have the ones place, the tens place, and the 100s place. So this number here is, of course, just the number we think of as 0. Now, I happen to have 3 zeros there, but we could throw away, that is, delete 2 of those, because none of the zeros to the left have any mathematical meaning. So we would just say 0. But they're still there implicitly. This, of course, is going to be the number 1. This is, of course, going to be the number 2, 3, 4, 5, 6, 7, 8, 9. And now something finally interesting happens. Once you hit the number 9, you can't count any higher using a single digit. So of course we have 10, but so we change the 9 to a 0. So then we have the number 10, where we now use a 1 in the tens place, but a 0 is in the ones place, right? Completely boring and completely familiar because all of us just take that for granted. But computers, again, only have zeros and ones in their alphabet. So how can they actually represent numbers like we use every day in a calculator? How do they represent letters of the alphabet or images or audio files? Well, let's just consider a slightly different approach here, where instead of having a ones place, a tens place, and a hundreds place, consider what that really is. That's technically, if we make this a little geeky, 10 to the 0 power, which is just 1, 10 to the 1 power, which is just 10, and 10 to the 2 power, which of course is 100. Well, now let's transition to using not those values, 10, but let's use 2 as a base. Right? We use 10 because we had 10 digits, 0 through 9. Computers have 2 digits, 0 and 1, so let's just change the base of those numbers from 10 to 2. And now consider what 2 to the 0 is. Well, that 2 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. So computers, even though they only have access to zeros and ones, they use them in exactly the same way, but they assign different meanings to each of those digits from right to left. So for instance, the number you now see on the screen is how a computer using 3 zeros would represent the number you and I know as the number 0. This, of course, is going to be, in computer speak, the number 1. And whereas in our human world, we would represent the number 2, for instance, with 2 fingers like this using unary, or the number 2 using decimal, a computer is going to store the number we know as 2 with this pattern of zeros and ones, 0, 1, 0. Why? Well, if you do the simple math, it's 4 times 0 is 0, 2 times 1 is 2, and 1 times 0 is 0, so we get, therefore, 2. How would a computer represent, using only zeros and ones, the number we humans know as 3? 0, 1, 1, right? So you just change that 1, 0 to as 1 now, because now you have a 1 in the 2's place, a 1 in the 1's place, which is mathematically going to give us 3. Now things get interesting. Just as things got interesting from 9 to 10, so in the binary world, where you have just zeros and ones, things get interesting now. How would you think a computer represents the number 4? 1, 0, 0. So we just flip those zeros to ones, and now we have 1, 0, 0. And so if we keep going here, how high can I count with just 3 digits in binary? 7, right? Because you can change all of these to ones, and at that point, if you do the math, that's just 4 plus 2 plus 1, which gives you, of course, the number 7. So binary, this language that computers speak and have always spoken, is not all that dissimilar to what you and I use as humans, but they just use it using a smaller alphabet, but exactly the same process. But of course, a computer isn't doing anything digitally like this. It's actually doing so with hardware. So how do we get to this conceptual idea of binary to very physical devices like your Macs and PCs and your phones in your pocket? Well, let's start calling each of these digits, these zeros and ones, or binary digits, what they're more conventionally called bit. If you've ever heard this word of bit, it just means binary digit. It literally means a 0 or 1. Now, of course, a single bit is not terribly useful in life. If you have just one bit, you can literally only count from 0 to 1, and that's it. So if you want to count higher than the number we know as 1, you of course need more bits. And the most common unit of measure is not to use a single bit or a single light bulb, as we'll soon describe it, but rather to use 8 bits or 8 light bulbs. Because in fact, what's neat about binary, and the reason computers use binary, is because if the only thing they have to do in life is store zeros and ones, you know what they can kind of sort of do? They can just treat zeros and ones like switches that are off or on, or maybe even like light bulbs. Like my phone's flashlight right now is off, so I could argue that my phone is a physical device that currently represents the number 0. But if I turn the flashlight on, you could argue that because I flipped the switch, now it's representing the number 1. And indeed, that's why computers ultimately use binary, because what is the only physical input to your computer? For instance, a desktop computer at home, or a laptop at the end of the day, or your phone overnight. What's the only physical thing you connect to it? Electricity, right? And so electricity is some flow of electrons back and forth, but it's either there or it's not. And so that's why computers, generally speaking, use this binary system, because if the only thing you have as physical input to the device is a flow of electricity or no electricity, you know what? We might as well describe that as having 2 possible states, off and on, or 0 or 1. But of course, just having off and on isn't useful, so most humans, when building computers, generally standardized on giving that computer at least 8 bits, or 8 light bulbs, or 8 light switches, minimally, to work with at a time. So instead of having them as being just single ones, we might have 8, and this might give you 8 bits, but there's a more conventional word that you probably do know. What is another word for 8 bits? A byte. So if you've ever wondered what a byte is, with just a Y, that is literally just 8 bits, which it means any old pattern of zeros and ones, but 8 of them in a row. Why 8? Well, it happens to be a power of 2, which is convenient, so there's hardware reasons why this is useful. But you're probably familiar with kilobytes and megabytes, and these days gigabytes and terabytes. Those are just more and more of these bytes. A megabyte is 1,000,000 bytes, a terabyte is 1,000,000,000,000 bytes, and so forth. So this is terminology you probably see and take for granted, but it really just reduces ultimately to these zeros and ones. So how about here a little exercise? I've got 8 light bulbs here, or 8 bits. 3 of them are turned on. And let's propose that a light bulb that's off is a 0, and a light bulb that's on is a 1. What number is being represented by these 8 light bulbs? 40 I heard, 50 I heard. Any other thoughts? How about a little guidance? If I do that, it's more than 3, but you continue the same pattern. 1, 2, 4, 8, 16, 32. What's that? I heard 49 here. I hear 50. So 2 50s, a 49, and a 40. 50. So now, okay, probably 50. Yeah, so it is indeed 50, but why? Well, one of the light bulbs is on in the 32's place. Another light bulb is on in the 16's place. So if you add those up, that's 48. And then a third light bulb is on in the 2's place, which gives you 48 plus 2 is 50. So literally, if you were to store the number 50 in your calculator or in your computer more generally, what's going on underneath the hood of that device, so to speak, is that there are 8 tiny little switches that are being turned on or off in this pattern, and that's why your calculator or your phone or your computer are currently showing the number 50. And what are those little switches called? If you've ever heard the term transistor, right? Anytime you've ever heard of Intel, the company that makes the brains of computers called CPUs, those things have billions of transistors in them these days, these tiny little chips. Those are essentially tiny, tiny, tiny little light switches that can be turned on and off. And so computers these days have way more than 8 bits or 8 switches or 8 transistors. They have millions or billions even, but that's how our computers today can do way more than just count up to values like this. All right, so let's maybe just to vary things here just for a moment. Can we maybe get 8 volunteers real quick just to come on up and hold sheets of paper? Anything? Okay, here we go. Number 1. Anyone? We only need 7 more volunteers. Okay. Number 2. Number 4. Thank you. Okay, number 8. Nice. Number 16. Good. 32. Oh, I heard a 64 coming up. And this is the biggest, best number. Anyone? Okay, 128. Okay, so if you all could just line yourselves up perfectly, exactly like that. That's amazing. Okay, make maybe a little more room over this way. So here we have 8 human volunteers who are wonderfully representing bits, if you will, within a byte. And right now all of their hands are down, when that's great. Let's just assume if someone's standing there like this, they represent a 0. But if they were to raise their hand, let's assume they represent the number 1. So maybe just a little challenge, a warm-up exercise. How would the 8 of you represent the number 1 in binary? Correct and correct? All right, how about the number 7 real quickly? Nice. Okay, how about a quick sanity check? Number 50? 32, a 16, and what? There we go. Good, good. Okay, good. Okay, hands down. How about 255? 255. 255. This is a lot of math. I'm hearing toda la gente? See? I think so. If we do the math, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 indeed is 255, which is to say, if you have 8 bits or 1 byte, this is as high as a computer can count, at least if we start counting at 0. In fact, just to be clear, how do we represent the number? Okay, we are representing the number 0 perfectly. So if you start counting at 0, as computers typically do, the highest they can count with 1 byte is 255. So how would a computer possibly count higher than that to like the number 256? You have to add another bit. So we would need another person. We would need someone to represent the 256 place. But to do that in the real world, you literally need new hardware, right? So it's no surprise that sometimes if your phone is old or you want to store more data on it, more large files, more photos or whatnot, you sometimes do need to physically upgrade because your hardware does not have enough of these bits, enough switches to represent them. And so that too is just one of the reasons why computers need to be upgraded over time to store more and more space. So perhaps a round of applause, if we could, for our volunteers. And you can keep those. Sorry, let me cut through here. We have a tradition back home of giving volunteers CS50 stress balls, if this might help with your studies. Here you go. Thank you. And who did I miss over here? I've got a couple more. Okay. I think, did I miss 1 or 2 volunteers who stood up but didn't receive? Yes? Okay, you too. Thank you so much. Okay, so at this point in the story, presumably most everyone knew that computers somehow speak this language called binary and only understand zeros and ones. But hopefully now you have more of an appreciation, if you didn't already, as to what that even means. Computers are not all that different, if you will, from you and I. They just have fewer letters of the alphabet to work with, but the process is exactly the same. But of course, computers can do so much more than store zeros and ones and store numbers, even though back in the day, that's how they got their start, by being calculators, just doing math. But today you can send emails, text messages, compose graphics, use Instagram filters, play video and audio. So how do we possibly get from just electricity to switches turning it on and off, to this notion of zeros and ones, to much more interesting applications of computing and computer science? Well, let's transition away from zeros and ones and consider the very familiar letter of the alphabet, like A. So a computer clearly, your phone clearly can express the letter A, but how? If all it has at the end of the day is patterns of zeros and ones, and we've already decided that those patterns of zeros and ones are used to store numbers, how do you represent A? Let alone B and C, let alone images. Any thoughts? With what? Identification, what kind?
Codification.
Codification. Yeah, so you can actually come up with some kind of coding that simply we all decide in this room, just as humans did decades ago in some other room, that you know what, if we only have bits to work with and therefore numbers to work with, well, let's just all agree that in the context of a program like Microsoft Word or an SMS program or WhatsApp or the like, in the context of a program that needs letters of the human alphabet, let's just all agree that the letter A in capital will be represented just because by the number 65. That is, we will just all agree in advance that 65 henceforth shall represent the letter A. And you know what? 66 is going to represent B. And 67 is going to represent C, and so forth. And we can come up with a codification of other mappings as well. And when humans did this decades ago, they called it, as you did, ASCII. It happened to be done in the US initially. This is the American Standard Code for Information Interchange, which is just a very wordy way of saying what you did, which is that it's just a coding from numbers to letters, so long as all of us and all of our devices agree on this, which they have because all of us use Microsoft Windows or iOS or Mac OS or the like. That's built into this coding into those operating systems. What are some of the other letters of the alphabet? Well, D might be 68, E 69, F 70, 71, 72, 73, and so forth. So let's consider one question. If a computer, in its memory, among its switches that are turned on and off, happens to be storing this pattern of numbers, 72, 73, 33, what message is that computer apparently storing? If it's 72, 73, 33, and here's just a partial list of the code. Yeah, so hi, at least HI, it's not obvious what the 33 is. Anyone want to guess? Oh, yeah, so it's an exclamation point. How would you know that? You would not unless you looked it up or knew it already, because humans decades ago just decided arbitrarily, but universally, that 33 shall represent the exclamation point. So if a computer is indeed storing 72, 73, 33, and it's in the context of WhatsApp or Gmail or some text-based program, those same patterns of zeros and ones are not going to be interpreted as literally 72, 73, and 33. That's not what we humans want to see on the screen. It's going to be shown as HI exclamation point. So on a typical keyboard, of course, you might have a whole bunch of keys like this, maybe a few accented characters here and there. But there's probably, certainly with multiple languages in the human world, more than 255 characters these days, right? We had 8 volunteers. The highest they could count is 255, but especially if you consider accented characters in some languages, if you consider certain Asian languages with all the more symbols, we have way more letters of alphabets in the human world than 255. And here you can see some American bias. Like, we only used 8 bits, technically 7 bits decades ago, because we were really only representing, at the time, American English in the US. So there's grown to be alternative systems, not just ASCII, but something that's more expressive that gives us things like accented characters on top of existing letters of the alphabet, but even these things. Right? I'm guessing these are as common here as they are back home. These are, of course, emojis, but what are they? They look like pictures, but they're not. They're actually characters in an alphabet. Because it turns out, a few years ago, humans decided to stop using only 7 or 8 bits, or 1 byte, to represent characters. We decided, you know what, let's sometimes use 8, like our volunteers, but let's sometimes bring another 8 people up so we have 16 bits. Or let's use 24 bits. Or let's use 32 bits. And if you have 32 bits, if we had 32 humans here, all with their hands up, anyone have a rough estimate of how high 32 volunteers could have counted? Shy of that, it's well, actually, more than that, more than 6 million. 4, yeah, so it's more than 4 billion. So once we had 32 people up here, they all put up their hands, and we did the very tedious math. At that point, you would count as high as 4 billion. Which is to say, computers these days are not limited to just what you see on your keyboard. You can even have characters like these. This is actually one of the reasons why we have all of these ridiculous emojis in the first place. We have so much room now in computers to represent characters. Heck, we might as well start having some fun with that. We couldn't have done that decades ago when we had only 8 bits. Now we can. And every year now, there's a whole consortium of volunteers that is releasing more and more of these emojis. So that new system is called Unicode. And it's a superset. It's bigger than ASCII, but it doesn't change A being 65 or B being 66. It just adds to those mappings for all of these additional characters. So this happens to be, at least in the world of iOS, the most popular emoji as of 2019. This is face with tears of joy. Does anyone want to guess what decimal number is used by computers and phones to represent this character here? No one's going to get this, I bet. And you shouldn't. A little high. It's actually 128,514. So you wouldn't know that, and you shouldn't know that, because this is what computers are supposed to be doing for us, implementing this mapping. But if you really want to take the fun out of receiving or sending an emoji, what's really happening when you send or receive an emoji, specifically that one, the face with tears of joy, your phone or computer is sending a very geeky sequence of zeros and ones from your machine to someone else's machine. And because it's in the context of a texting program or WhatsApp or the like, it's being interpreted as not 128,514, but as a picture that should be displayed on the screen. So context matters based on the program.
How can the code tell when I wanted, for example, showing 65, how can it tell that I wanted to show the number 65 as opposed to 8?
Really good question. How does the computer know when looking at some number of bits whether you, the human, want to see 65 or the letter A? It's entirely up to the programmer. So the person writing the software, whether it's Microsoft Word or Gmail or WhatsApp or the like, has to decide in their code, in the language they're writing, whether to show some value in the computer's memory, either as an emoji or as a letter of the alphabet or as an actual decimal number, as in a calculator program. So once you learn how to program, this is exactly one of the decisions you have to make when writing code. You have access to all these zeros and ones in the computer that you can store information in. You have to decide how to use it. And it just depends on context, ultimately. So let's consider something more interesting even than text. We started with electricity. We then had zeros and ones, or decimal, or now we have ASCII or Unicode on top of it, so to speak. What about colors? Well, you might have been generally familiar with this acronym, RGB, red, green, blue. So so that's an alternative. CMYK is another way of representing colors of the rainbow. Many computers still use RGB, which stands for how much red, how much green, how much blue do you want? Because if you combine those three colors by overlapping different amounts of them, you can literally get any color of the rainbow. But it's RGB because you specify for the computer how much red you want, how much green, and how much blue you want. So for instance, if this is, for instance, just placeholders for our RGB, suppose that in the context of Photoshop or any other graphics program, the computer happens to be storing the equivalent of the number 72, 73, 33. In the context of a text message, that's going to say hi. In the context of Photoshop, though, that might say, I want 72 amount of red, 73 amount of green, and 33 amount of blue. Now, what does that mean? Well, per our volunteers, the lowest we can count is 0. The highest we can count with 8 people was 255. So 72 and 73, that feels like a medium amount of red and green. 33 of blue feels like a low amount of blue. So what do you get if we combine a medium amount of red and green and a small amount of blue into just one dot on the screen? Any ideas? Brown? Yeah, so it's actually pretty close. Brownish orange or a little more yellowish. If we combine those three amounts, what we actually get is a single dot that's this like brownish yellowish color. So that is to say, this shade of yellow, if being stored in an image you're looking at on the screen, very specifically is the result of three numbers, 72, 73, 33, or 8 plus 8 plus 8. So 24 bits total being allocated by the computer just to represent that single dot. Now, what is that dot? That actually, too, has a name that you might be familiar with. So pixels. A pixel is just a dot on the screen that you can kind of see if you bring your phone or your laptop really close to your face, or even your TV these days. But honestly, if you have like a Retina display or a very fancy or new Mac or PC or phone, odds are you probably can't even see these dots because they're so small these days, but they are there. Every image on a screen is implemented with what's called a pixel, a dot, and every pixel is stored using probably 24 bits. So with this, that is to say, with our 8 volunteers, we couldn't even really represent a single dot on the computer screen because we'd need 16 more people just to express a single dot. Now, to be fair, way back in the day, black and white images were a thing, and that was great because how many bits do you need to represent two colors, black and white? Just one, so that was 1-bit color. These days we're up to 24-bit color, if you've ever heard the term. That just means you have access to millions of colors, not just black and white. So if we consider now the actual emoji, recall that this thing had lots of yellow in it. And if you zoom in on an emoji like this, and we go far enough, you can actually start to see those dots. So this is to say that the emojis, or any image or photograph that you see on your screen, is composed of thousands, maybe millions, of these little dots on the screen. And every one of those little dots requires, it seems, 24 bits to represent, or 24 people to represent every little dot on the screen. So this is why when you have a very high resolution image from your camera or your phone, it takes up more and more space because you literally need more zeros and ones to represent all of those additional dots that you captured with your phone or with your camera. So what about this? So these are back in vogue. This is an animated GIF, or a graphic format that just kind of plays kind of like a movie, but a very cheap movie in that it's very low resolution. But it's a video nonetheless. And what is a video then? Yeah, a bunch of frames, but frames, what do you mean by frames?
Still images, one after another.
Yeah, so, and this is really thematic in computer science. Once you understand like one idea here, you can use it as a building block, so to speak, to build something new and more interesting on top of it. So if we all understand roughly what an image is, it's a whole bunch of dots or pixels, and every dot or pixel needs, say, 24 bits to represent some red, some green, some blue. The next sort of conceptual evolution of that is, well, if I have one image, but I want to animate it, why don't I just get 2 or 3 or 10 or maybe 29 or 30 images and just show them to the human really fast, one after the other? This is a video of images, really. You're seeing probably, this is pretty low budget here, this is probably like 10 images per second, give or take. A standard Hollywood movie might be 30 frames per second or 24 frames per second, which just means show the human audience 24 or 30 images rapidly over the course of a second. So this too is a theme of computer science, this idea again of building blocks and abstraction, where you take one idea that at first seemed really low level, like zeros and ones, but then you build on top of it, build on top of it, build on top of it, until now we're already having a conversation about how computers represent video. All right. So that's then how we might represent inputs and outputs, but what remains in that black box in between, right? That's really the more interesting part, the more thoughtful part of computer science is how you take inputs, the problem you have, and produce some output from it. So let's consider what's inside of this box, and this is what a computer scientist would call an algorithm. An algorithm is just a term for step-by-step instructions for solving some problem. So that's all an algorithm happens to be. And there's a lot of algorithms in the world that we humans have solved for some time, but also our computers have been doing the same. And let's consider one of the oldest school ones here. So odds are most of us don't even use this technology anymore. This, of course, is a phone book with lots of names and numbers. Those names are probably alphabetized from A to Z so that I can look someone up quickly. Now, even if none of us really use this technology anymore, in fact, it was actually very hard for us to find this phone book for this demonstration, we all use the same idea, right? Whether you have Android or iOS or something else, if you pull up your contacts to send a text or make a phone call, and you scroll through them, well, frankly, that's really just like flipping through the pages of the phone book, albeit more efficiently. And if you use autocomplete and start typing someone's name, and immediately you see the answer, well, that's the same thing as solving a problem. The input is the name, the output is hopefully their number, and I dare say this technology worked exactly the same way. So suppose I'm looking for a friend like Mike Smith. His last name is Smith, starts with S, so I could start looking for him by opening the phone book, and looking on the first page, I don't see him. Second page, I don't see him. Third page, I don't see him, and so forth. So step by step. This is a step-by-step process. It's an algorithm. Is it correct? Will I find Mike Smith if he's in here? Yeah. But you eventually, and that's probably your hang-up, like this is pretty dumb way to find Mike Smith because it's going to take forever. So that's fine. Why don't I do it instead 2, 4, 6, 8, 10, 12. It sounds, and it is, twice as fast. Is that algorithm correct? Might miss him. Why?
Might skip his name on one of the 2 pages.
Yeah, eventually I might get unlucky and he just gets sandwiched between 2 pages. Is it solvable? Well, yeah, because maybe if I get to someone whose name starts with T, okay, maybe I can like back up 1 page, maybe a few pages, but not dozens or hundreds of pages. So it's fixable, but it is buggy. That is, it has a mistake in it. But none of us, honestly, are going to do that. And our phones don't do that either, most likely. How would you find Mike Smith more intuitively in this thing? Yeah, so ideally, yeah, just use the index. But barring that, go. All right, so I don't see the letter S, but be more specific. All right, somewhere. All right, I'm in the M section, so roughly in the middle of the phone book. And now let's suppose that I'm looking for Smith indeed. His name starts with S, so where is he? Is he to the left or is he to the right? So he's obviously to the right alphabetically. So what does this mean? Well, at the moment, I have 1,000 pages, for instance, of a phone book, really thin pages, on which I'm trying to solve a problem. But I now know with this instant decision that Mike is not to the left, he's necessarily to the right, which means I can literally tear the problem in half, throw half of the problem away so that now I'm down from a 1,000-page problem or input to a 500-page problem. But consider the alternative. The first process I used was really slow. It took a 1,000-page problem and turned it into a 999-page problem, and then a 998-page problem, and so forth. The second algorithm was better, but consider that it went not from 999 to 998. Oh, sorry, a 1,000-page problem. Suppose that the phone book had 1,024 pages, for reasons that are mathematically useful, instead of 1,000 pages. And I started tearing one page off at a time or flipping through, you can see that I'm not really making that much progress. The second algorithm was better, but even visually, it doesn't feel like that much more progress. I go from 1,024 to 1,022 to 1,020, but it's not really going fundamentally faster. But if instead I continue with this logic, I've split the phone book in half, now I go roughly to the middle here. Ooh, I went too far. I'm in the T section now. So if I'm in the T section, is Mike to the left or to the right now? Now he's to the left, so I can again tear the problem in half, dividing and conquering, if you will. Now I'm left with 250 pages only, and I can continue this process again, and again, until hopefully I find Mike on just one final page. Of course, I can never look for anyone else again in this phone book, but I found him so much more quickly. And consider visually the impact of that. If I'm now dividing and conquering, dividing the problem in two every time, not just 1 or 2 pages at a time, I can start at the same size phone book, 1,024, but go to 512, 256, 128, 64, 32, 16, 8, 4, all the way down to, hopefully, just that one final page, and then I'm done. But consider the other two algorithms. At this point, I still had 1,000+ pages left. And this is why I wanted to start at 1,024, because the math works out to be super pretty. But the point is that how many times can you divide a phone book in half that has 1,000+ pages? Sorry? Logarithmically, or more specifically, roughly 10, give or take, times before you finally have found Mike Smith if he's in that phone book. But that first algorithm would have taken 1,000 steps. The second algorithm would have taken 500 steps, which is to say that just with a little bit more familiar human thought, you already can solve these problems so much more efficiently. And now if we try to analyze it, and a computer scientist, when trying to make an argument that their code is better than someone else's, might even do something like this. We don't have to get into the weeds of mathematical formulas, but just to draw a general picture. A computer scientist might now analyze that algorithm by drawing a picture like this, where we have on the vertical line the amount of time it takes to solve the problem. On the horizontal axis, the size of the problem. And the size of this problem would have been measured in pages of the phone book. And the vertical might be measured in seconds or tears. So some number of steps. Doesn't really matter so long as we just agree on some units of measure. So the first algorithm, where I was turning one page at a time, might be represented as n. A computer scientist usually uses the letter n to represent any number. And if the phone book had n pages, it's a straight line relationship. Because for each additional page in the phone book, it might take me one additional step or page turn. The second algorithm was a little better, but it's still a straight line. The slope is just lower, but it's almost the same fundamentally. Why? Well, consider just this dashed line here on the overhead here, which shows for some number of pages, it might take me this many steps here. But if I continue with the second algorithm in red, it might take me that many more steps. So this is to say that the shapes of the lines are the same, but the yellow line is halfway below the red line. So that's definitely faster. It is definitely faster. It's twice as fast. But that third algorithm that was called logarithmic, as you say, or that has more of this fundamental impact, bigger bites out of the problem at once, has a fundamentally different shape. This is called a logarithmic graph, and it just has a very different curve shape that's significant because it goes up and up and up so much more slowly than either of the other two algorithms. So suppose, for instance, we didn't have this phone book, but suppose that we had a phone book that was twice as big, 2,000+ pages. The first algorithm would take an extra 1,000 steps just to find Mike Smith potentially, because I have to flip through twice as many pages. The second algorithm might take another 500 steps because, again, if the phone book is twice as big. But the third algorithm if the phone book is twice as big next year, because a lot of people move into town, how many more steps will my third algorithm take, even if the phone book is 2,000 plus pages? How many more steps? Yeah, just one extra step, right? Because if you hand me a phone book with 2,000 pages, no big deal. I can tear it in half after looking left or right for Mike Smith and throw away 1,000 of those pages. So this intuition that you probably already have if you pick up a device like that is exactly what iOS or Android do when searching your contacts when you start auto-completing someone's name. They could just search top to bottom, but that could take a long time if you're looking for someone with a name that starts with Y or Z. But they could instead use this algorithm, now known as binary search, bi meaning two, hence splitting in two, that would find that person fundamentally faster, as is evinced by this shape of the line. So now let's just formalize this to see where the connection is to programming. So we did all of this verbally and physically, but a programmer ultimately needs to transcribe their ideas to some kind of format that a computer understands. And there's a lot of languages out there, C, C++, Java, Python, PHP, Ruby, and dozens more these days that are still in play. But let's just use something more generic. Let's use something that we'll call pseudocode, which is just a language written in English or Spanish or any human spoken language that they just use to kind of casually but precisely convey their ideas. So how might I convey that algorithm for finding Mike Smith? Step one might be, as I did, to pick up the phone book. Step two might be to open the phone book to, say, the middle. And then now I have to make a decision, right? I have to take a look at those names, and I have to decide, do I go left or do I go right? So how might I express this? Well, I'm going to look at the page. I might then ask myself, if Smith is on the page, what do I want to do? Stop and probably call him right away. So you know what? Because that's conditional, that depends on my answer to this question, I am going to, by convention, just indent that line, number 5. But if Mike's not on that page, I have to make a different decision. If Mike is earlier in the book, to the left, what do I want to do then? Well, I can tear it dramatically in half, but fundamentally, I'm going to do the exact same thing, but just on the left half of the phone book. So what am I going to do? I'm going to go open to the middle of the left half of the phone book, and then, turns out I already know what to do once I'm there. I can just go back to line 3, or step 3, because it's the same problem, it's just smaller. But suppose Mike's not to the left. Suppose he's to the right. The question I then have to ask is, maybe I should go to the right, so I should open to the middle of the right half of the phone book, and then what do? Exactly, go back to step 3. It's the same algorithm again and again, but powerfully, the input is getting smaller and smaller. Otherwise, there's a fourth and final case. If Mike's not on the page, he's not to the left, he's not to the right, maybe he's not there, so we should write code to handle this situation too. So I might say else, you know what? Go ahead and just exit or quit the program. Now, as an aside, on your Mac or PC or phone, if you've ever gotten like a little beach ball or hourglass that spins forever, or your Mac or PC freezes for some reason, quite possibly that's just the result of even a situation like this, where a human programmer was writing some code and they didn't realize there's a fourth case. Because if you fail to write code and consider what might happen in all possible inputs, honestly, it's not known sometimes what the computer will do. Maybe it will keep hanging, maybe it will crash, maybe it will reboot. That kind of behavior can be undefined. And so that's why even for something like this, where it should go without saying that you should stop looking for Mike if he's not there, you have to tell a computer to do that. And so in programming, while it's wonderfully powerful, it really is a process that requires that you first start to organize your thoughts better, communicate more efficiently and more logically and clearly, so that the instructions you convey to the computer are ultimately properly executed. And so let's actually go ahead and do this as follows. It turns out that within this program, there's a few representative ideas of any programming language, be it Java or C++ or anything else. Highlighted in yellow here are what we would call in computer science functions. These are actions, these are verbs, these are things you do to achieve some goal. Also now in yellow are what we're going to call conditions. Conditions are questions that you ask yourself that allow you to decide whether to go left or go right or do something else. So it's a branch a fork in the road, if you will, a branch on a tree. You can go in different directions. How do you decide what direction to go in? Well, the thing highlighted in yellow now are literally the questions that have yes/no answers. Smith is on page. Smith is on earlier in the book. Smith is later in the book. Those are questions you could ask yourself to which the answer is necessarily yes or no. or if you will, true or false, or heck, if we only have two words, 1 or 0. So even in programming, do you see hints of that binary system yet again? Lastly, there's one more thing here. What might we call these highlighted lines that make us do something again and again? A loop, a cycle, yeah, in programming you would call it a loop, and that's just another piece of programming via which you can solve some problem by doing something again and again, which is to say that in most programming languages you have at least those 4 features. And we've not looked at a programming language per se. We looked at pseudocode, some Spanish-like syntax that just conveys the idea, but it's ever so important to do things precisely. And so we thought we'd try to emphasize this ultimately with one goal, one human program that just requires a few ingredients, literally here. If I can go over here, we have a few ingredients here for which we now need some instructions for making a delicious sandwich. Of course, most of this should go without saying. It should be pretty straightforward how to make a sandwich or how to tell another human how to make a sandwich. But in the spirit of programming and beginning to think like a computer scientist, perhaps we should take care to do this ever so precisely. So let me I'll play the role of the computer that takes its instructions literally as input. If you all wouldn't mind, maybe one at a time, offering up instructions for how to make a delicious sandwich. I have some bread here, knife, a plate, and some spread here. What should step 1 be? Open the bag. That is through the... Oh, untie the bag. Okay, so if I may. So our first opportunity to be more precise. So untie the bag. Okay, step 2. Okay, now, open the... Through the opening, thank you. Okay, step 3. Grab the first slice. I hate this slice, but okay, but discard it because it's disgusting. Okay, so we'll put that over here. Sorry, say it louder? Put it on the plate. I was told to discard this bread because I don't like the end, so what should I do next? Take the next one, thank you.
What if we take out both, 2 of the pieces we'll need at the same time?
Okay, I'll take out 2 at the same time. Put them both on the plate. Do you want me to take a loop? Go ahead. Okay. We could. So yes. So you could. This was an opportunity for a loop. Many programmers, if it's such a small piece of work, like just 2 things, they might just write multiple lines of code. But absolutely, that could have been a loop that executes 2 times. But now we're at this point in the story where I do have 2 out, and I heard put it on the plate. Put it flat on the plate. Okay. Next step. Open can. Grab whatever I need to open the can. Okay. Okay, and now I'm opening the can. Thank you. Gently pull back. Discard that. Take a knife. By the handle. Okay. Thank you. Grab some. Oh, with the knife. Okay. Got to be precise, though. Okay, with the knife. Oh, sorry, next. Rub a small quantity on the bread. Spread it gently on one slice. Oh, gently, gently. Okay. Only on one slice. On one, okay, so yes, so I'm still doing this. Until the surface is covered. Then stop, thank you. Okay. And next? If there's a good condition. Go back to line. Grab the handle, thank you. Okay, so if there's another slice, repeat what I did on the first slice. So take a small amount of this, spread it gently on the bread. arguably, yes, but until it's covered smoothly, and then put it down, I think was the step. Now what? Sandwich it? That's okay. Take both slices.
And put the spread together.
Put the spread together slowly. Cinematically.
And then put it flat on the ground.
I think, okay, thank you. All right, I think we're done. So, thank you. So, this is just a taste, literally a taste of computer science, pun not intended. Just a taste of computer science. This course that we happen to teach back at Harvard is called CS50. It is freely available online, and indeed among the final questions for the day is, among the final goals of the day is to encourage you, whether it's to take this class or to take some other class in computer science, but really to consider taking a class that up until now might have been not on your radar, might not have been within your comfort zone, because much like I, back when I was in college, did not really think of myself as a computer scientist, found myself wonderfully surprised by just this or perhaps any other field. So happy to take questions, but it's been such fun to be here with you today. But this is a bit of computer science. Thanks.